About a number of tools that we've developed for exoplanet science in my group at UNLV, and I'll mix in a few other things as we go, just so that I can advertise some other things that are going on. The first one, okay, so there are basically four main areas where we've developed new software. There's software for planet interiors. Okay, it does show up, good. Whoops, what I meant to do. There's software for planet interiors called Magrathea. We have stuff that works on, that we can use for planet formation, especially for planetesimal accretion. And then we have stuff to model dynamical evolution. This is all code that's been developed for rebound. And then at the end, we have this code that does the composition of planetesimals, that does the chemistry of the protoplanetary disk. So all of these are different codes that we've been working in our group at UNLV and with a number of collaborators. The first thing I wanted to mention is that there is this paper that just came out by Jack Lissauer that's an updated catalog of the Kepler database. So this one is accounting for changes in the orbital period that come from transit timing variations and have updated stellar properties from the Gaia mission. So this is now actually available. It was a number of years. I think we started before COVID. I think we started on it before Kepler ended. So it's been several years in development, but it's now available. All right. So the first thing I want to talk about is our open source. All of our code, if it isn't available online right now, I think everything is available online. It will be. That's the goal, is to have all of this stuff available for everyone to use. So Magrathea, it's an open source planet interior structure code that is spherically symmetric. It was developed by my first postdoc, Chen-Liang Huang, and David Rice, who is now a postdoc in Israel. He was my graduate student. He was my undergraduate student and then my graduate student. So the goal with Magrathea, the design criteria that I gave to Chen-Liang was, I want undergraduates to be able to use it within a day. So it's one undergraduate day to ramp up and get the code running. It has the ability to change around the equations of state. So I'll show kind of what I'm referring to there, where you just like comment in the one that you want, or like just put it in. So it's real easy to modify how the model runs. And then right now it's a 4-layer planet structure. We're currently working on mixing between the layers. Right now they're separate layers. And the goal was to make it easy to modify so that we could more effectively collaborate with the high-pressure physicists that are at UNLV. So we have a fairly large high-pressure physics group at UNLV. I don't know if anyone is familiar with some recent controversies that have happened in high-pressure physics. I can tell you about that at another time. But there is a large group of high-pressure physicists at UNLV. And so one of the things that I wanted to do when I arrived there was, how do I collaborate effectively with everybody that's in my department and in the other departments at the university? And so being able to incorporate new equation of state measurements was part of the reason that we built this. So the way that what this takes as input is, what are the layers that you include? We have a core, a mantle, a water layer, so a rocky mantle, a water layer, and an atmosphere. The atmosphere model is not very sophisticated. We have two models. It's an isothermal model, and another one's an ideal gas. We have another atmosphere model. We have two atmosphere models that work on here. That was the last thing that was developed, and we're still, we haven't spent a whole lot of time making it more sophisticated because we're focusing more on what happens. It's mainly for modeling super-Earth planets and not like gas giants and stuff. Between each layer, there's a temperature. You can include a temperature jump, and then you just tell it how much mass is in each one. You feed it an equation of state, or a phase space diagram, which says, what phase is the thing in, depending on the temperature and the pressure. And one of our goals is one of my goals is to make it so that you can give it a JPEG, like you just cut and paste from a new journal article that has a phase diagram, and then you just like put it and feed it in the JPEG, and it will map out the boundaries for you. We haven't gotten to that point yet, but we've tested some prototypes on that. But the goal is to make it so that you can hand draw your phase diagram and feed it in and then have it run. So We're getting there. And then it will return the interior structure and like what's the temperature and pressure as a function of, you know, radius from the interior. It's fast. So this is a comparison between it and Exoplex, which is another kind of interior model. And we basically get the same structure in terms of what does the planet look like at different distances, and it runs about 5 times faster to get through it. We have some tools for plotting, like these ternary diagrams, but this shows basically how fast or how long it takes to run a single model, which is a few tenths of a second to get through it. Part of the reason for that was so that we could use it for Markov chain Monte Carlo without having too much overhead. Also, so that we could do proper like error bars, doing phase space mapping and things like that, including systematic uncertainties in a bunch of different parameters, so that we could get a better handle on what constraints we can place on the interior properties of the planet. And one of the reasons why this is important and will become more important in the future is this shows the mass radius relationship for different planets with 100% iron core, 100% mantle, and 100% water. And this, what's shown here are different equations of state that are measured by different experimental groups from around history and from around the world. And you can see that the experiments there's some variation between them. The variation is significantly smaller than the error bars that are reported in the experiments. And while there aren't very many 100% water planets that are out there, I'm sure, but we're looking at more than, we're getting close to 10% difference in the size of the planet that results from the different equations of state that are reported in the experimental literature. Now, 10 years ago, when the uncertainties in the planet sizes were like 20% because it was dictated by the uncertainties in the size of the star, this wouldn't have been important. But with adding Gaia data to the mix and adding astroseismology for getting stellar sizes, fairly soon we're going to run into the situation where it's actually the experiments that are the biggest source of uncertainty and not the astronomy. It's a rare circumstance to be in, but that's the direction we're headed, and so we're going to have a better interface between the exoplanet community and the high-pressure physicists going forward. So let me look a little bit about this water, because this is one of the things that we tackled at UNLV. So with water, water is an unusual molecule. So it goes through a number of different phases when you compress it and as you change the temperature. Right now, there's something like 15 known phases of water ice. But part of the reason that it's weird is that it has different ways that the bonds form. So at low pressure, the bonds form, it's hydrogen bonds that form the solid. And as you increase the pressure, you switch from hydrogen bonding to covalent bonding, and then as you continue to increase the pressure, you switch from covalent bonding to ionic bonding between the hydrogen and the oxygen. And so if you look up here, at high temperature, you go from a liquid and then you'll go into different solid phases, ice 6 to ice 7. So ice 1H, this is what we get on the surface of the Earth, because you're cooling the temperature down. But as you increase the pressure, so as you go towards the interior, you're going to go through ice 6 and then ice 7 and then ice 10. So this is hydrogen bonding this is covalent bonding. Ice 7 is, I don't know what the bonding is for ice 6. It's fairly narrow at ambient temperatures. It's a fairly narrow window where ice 6 is the phase. Ice 7 is covalent bonded and ice 10 is ionic bonded. And this transition for ice 10, okay, this is what I just said, where you have, so here's the covalent bonding, and then you switch to ionic bonding as you squeeze the oxygen lattice closer and closer together. So there's quite a bit of discrepancies between different studies, measurements of where this ice 7 to ice 10 transition happens. And it's important because ice 10 is less compressible than ice 7. And so if you run into ice 10 at lower pressure, then your planets are going to be bigger because they're harder to squeeze. And so if you mismeasure where the ice 10 transition is going to be, then it's going to introduce a bias in your modeling for matching, how much water content does a particular planet have to have in order to match the observations. And the discrepancy is, there's like a factor of 3 difference between the lowest and highest measurements of where that transition takes place. And these are all, I mean, these are all incorporated into planet models. And so our planet models disagree with each other because they use different equations of state, and then the equations of state disagree with each other. So the way that you make these measurements is with a diamond anvil cell. So this is this little contraption that's about yay big, like the size of a potato chip. And then you probe it with laser beams. So you have a diamond in each side, like in each of these things, there's a little diamond there. You cut the tip of the diamond off so you have a flat surface, and then you put a little gasket in there, and then you squeeze your sample in between there, and then you fire laser beams in there and interrogate the sample with these different laser beams. So this is what the diamond anvil cell looks like. You apply the force on here. You have a gasket that keeps the sample in between the culex, which is the surfaces. And then you'll often put a pressure, a known sample in with, so you'll have your sample that you're testing, and then you'll have a flake of metal or something like that where you know its properties, so that you can measure the properties of the metal and then use that to, like, you can measure the pressure and temperature conditions for the metal because it's a known substance, and then that's how you can calibrate what you're doing with the sample. And what we've been doing at UNLV is you put the water in there, you squeeze it, turns into ice, and then we can heat it with a CO2 laser. CO2, it's going to resonate, like the wavelength is in the infrared, and that's where the where the water molecules are going to start flopping around, and so you can heat the sample using absorption in the infrared. So one of the challenges that you face is, like, how do you measure the size of the box? How do you measure the crystal lattice size? And the way that you do that is with X-ray diffraction. If you have a single crystal, then you get dots like this. But typically what happens is single crystals are not easy to come by, and so you'll pulverize your sample. If you're doing a metal or something like that, you'll put in, like, you'll pulverize it into a bunch of small crystalline domains that are randomly oriented, and then instead of having a single dot, you'll get a bunch of rings, because you get the same diffraction angle, but now it's a random orientation, and so then it'll a ring from all the, thousands or millions of crystal domains that you're sampling. So then you fit a circle to this, and that tells you the crystal lattice spacing because it gives you the diffraction angle from the Bragg diffraction. So this is what we typically do with samples. It's under fairly rare circumstances where you'll actually get a single diffraction spot. So this is water. If you just put water in and squeeze it, then you get an ice crystal, and then you'll have something that looks like this. And then you fit a circle to these. Okay? It looks fairly easy, and it is fairly easy. The problem is that these are big blobs. They're not, they have a shape to them. They call it textured. And the reason that you get shapes like this, where it's not really a ring and it's not really a dot either, is because when you squeeze it, you get a bunch of different crystal domains that are randomly oriented, and they're different sizes, and you get only a few of them because your sample is not very big to begin with. So you have a few large domains, and then instead of having like thousands of them that are randomly oriented, you'll have 10, and then you get 10 dots, and then you fit a circle to it. The other thing is that when you have these things that are kind of randomly oriented like this, and you squeeze it, you're going to get pressure gradients. Like, as they run into each other, they're going to compress along those boundaries, and it'll distort the crystal, and that stretches out the dots. So instead of single points, you're going to get like these ellipses, and then, so all of that stuff contributes to adding systematic uncertainties to the equation of state measurements. So what you really want to do is have something that looks more like this, so that it compresses more uniformly around it. So this is done, this kind of regularization is done all the time in metallurgy. So I'll skip over this. But what we do is we squish the sample, and then we hit it with the CO2 laser and melt it, and then we turn the laser off, and it recrystallizes really quickly. And when you freeze something very quickly, you get small crystals. That's why you don't let your ice cream thaw on the countertop and then put it back in the freezer, because you get large crystals, and then it doesn't taste very good because it's got the wrong texture. If you want to make ice cream, you have to freeze it really quickly so that you get small crystals, so that it has a smooth texture. So you turn off the laser beam, it recrystallizes really quickly, and then you can bask in the amazingness of the small crystal grains to be able to make your measurements. And so the difference between what has traditionally been done in the field and what we're doing at UNLV is this. So this is history, and this is what happens when you do this laser heating technique. So this was a new thing that was developed in our labs with my collaborators, and it made a huge improvement in the equation of state measurements because you can measure the size of the domain as you compress it, the size of the unit cell. Then you can probe it with a number of different techniques that aren't really that important here. So what we found when we did this was there's actually three different, there's a new crystal structure, there's a new phase of water ice that's not on that original diagram. Basically what happens is you have regular ice 7 at low, so this is pressure on this curve, or on this axis. You have base ice 7, you compress the ice 7, and then you can actually see it's a cubic, ice 7 is a cubic structure. You can see the cube collapse. So it collapses in one direction, and then you continue to compress it so that it goes from a cube to a tetragonal phase, and then it goes through another transition when it goes to ice 10, and it collapses the rest of the way. So it collapses in one direction first, then you continue to compress it, and then it collapses in the other directions. And so another thing that was really beneficial between the collaboration between the high-pressure physicists and the exoplanet scientists is that high-pressure physicists, like high-pressure physics is an old science, and so they often are bringing along a bunch of data analysis methods from back in the day, and exoplanets is a bit younger, and so we have at more ready disposal better ways to analyze the data to incorporate systematic uncertainties, like with Markov chain Monte Carlo, and incorporating systematic uncertainties like the hierarchical Bayesian analysis and things like that. So we updated the data analysis methods that were being used to make better measurements of where these phase transitions happen. So there's a bunch of parameters that were added in our model. We had 3 phases. We have 2 phase transitions. And then we had a pressure-dependent systematic uncertainties, because as you keep adding pressure, you keep getting those distortions until you do the next laser shot to re-regularize the crystal domains. So doing all these things, we ended up with a new measurement of the location for the transition between ice 7 and ice 10, and it's below all of the previous reported results. So if you look on this axis, like way down here, because this is the temperature, so this was all done at room temperature. And so here is where the phase transition happens at 30 GPa, as opposed to 120 GPa, which was some of the other measurements were way up here. Having the measurements that were this low actually makes a number of improvements in the theory as to like why. So the issue was that it's really unusual to have, if you were to have this transition instead being up here at like 80 GPa, then the phase boundary between the ice 7 and ice 10 has the wrong, like the Clapeyron slope is going the wrong direction. It's not that it's unheard of, but it's unusual. And having it at having the transition to lower pressure requires a lot less explanation by the theorists as to why it's doing this. Now, one of the things that's interesting about having this phase transition between ice 7 and ice 10 so low is that when you're looking, so here is where our model fits relative to 2 common water equations of state that are used in planetary interiors, and we end up going between them. What's included here is the 1 sigma uncertainty in our equation of state. So the gray band is our 1 sigma uncertainty. But what it shows is that you can get quite a bit of difference between the previous measurements and our measurements. So back to this, when we feed it into our Magrathea equation, like our planet interior model, that when you're looking at things, at planets that are between like 0.1 and 10 Earth masses, so rocky planets, that this new phase of ice 7, like the collapsed ice 7, is the most common phase of the ice inside the interior of the planet. So it does depend on the fraction. So I think this was for a 50% water. This is like Ganymede. If you had the equivalent of Ganymede, but it was one Earth mass, then a substantial fraction of the radius would be this phase of water. And it's not until you get quite a bit more massive than a single Earth that you actually get the ionic bonded. So it could matter, especially if you're looking at magnetic fields, depending on how the magnetic field is generated. If it's generated like we assume it's generated in Neptune and Uranus with superionic phases, then where this transition happens also means that the superionic phase probably happens at lower pressures as well. Okay, so Magrathea, and this is the reason we developed it, was to be able to have this more rapid interface between the groups at UNLV. So the rest of the development that I'm going to talk about, a lot of it has been developed for Rebound, which is this N-body integrator that Hanno Rein has developed over, Hanno Rein and a number of collaborators have developed over a while. There's a number of advantages to working with Rebound. And so here's where you can find it if you're ever looking for it. So these are things that we have added to what's called, so Rebound X is the extension libraries. It's like, I want to add a new force. I want to include something that's not just typical gravitational interactions. And so you go to the extension library, and then you can add that force through that library. And so we've added the Yarkovsky effect. The Yarkovsky effect is when you have an object that's illuminated from one side, so now you have a hot side and a cold side, and then the radiation that is emitted by those two sides is going to have a different spectrum. It's going to have a different, basically different radiation pressure from the emitted radiation. And so depending upon the direction that the object spins, you can get a thrust that causes the orbit to increase its energy, or you can get, if it's spinning retrograde, then it will cause it to decrease its energy. That's the Yarkovsky effect. So we've added that. That paper just came out a few months ago. A few years ago, we added tides. So this is stellar and planet tides to it. It's a fairly simple tidal model, but it's in there now. And then we added this tool down here, which I think is probably one of the most useful ones. It's a general parameter interpolation tool, where if you have a parameter that's going to evolve with time, so it could be gas drag, it could be luminosity, it could be whatever, this is a way to add the evolution of that parameter directly into the integration without having to calculate it at each step. So in particular, we wanted to do stellar evolution, so we wanted to have the changing mass and changing radius of the star and the changing luminosity. But the time steps that you use for modeling the star are going to be different than the time step that you use to model the dynamics of the planets. And so this allows you to just run the stellar model, make a file that has, like, here's the time and here's whatever parameter you care about, like the stellar radius. Just have a 2-column file, and it will interpolate between the points and say, oh, at this time step, this is the stellar radius, and then at this time step, this is the stellar radius. So it runs, it allows you to do them kind of asynchronously. You can run multiple stellar models and then put it into the same integrator and have it run. So that's another thing that we added. These two things are in the same paper, the tides and the parameter interpolation, and the Yarkovsky's one. Another thing that we've done is we added collision fragmentation inside Rebound. This code already exists for Mercury, the integrator Mercury. John Chambers did it at like 2012 or something like that. And so this is basically the same software, like the same physics, the same parameterization, the same kind of results, except that it's in the Rebound package now. So this was done with my former graduate student, Anna Childs, and she did a lot of the development after working with Alyssa and Tom on some things. We're like, oh, so that was a good experiment. We did it with the Mercury integrator. Now let's port it over to Rebound so that we can use it with some of the other tools that we've been working with. So it's a collisional fragmentation code. Now, this is not part of the Rebound X extension. You have to just get the code directly because it's an actual modification of it doesn't work under the Rebound X framework. So it's a standalone version of Rebound. But anyway, so it has this collisional fragmentation. In this case, all of the bodies are uniform in their composition. And so most recently, it's a paper that we have just submitted. We've submitted it, we got the review back, and now we've resubmitted it, is collisional fragmentation between differentiated bodies. So now we're assuming 2 layers, and then we have a like a formula or a recipe for how much core material and how much mantle material is going to be ejected depending on the objects in the system. Now, I will say that this was, we came up with a recipe that has not been tested against SPH calculations. It's like we said, okay, when you have a collision, and here's where the impact parameter is, and here's the core size and the mantle size, roughly how much do we expect it to be? And these are adjustable parameters. So you can go in and say, actually, I want to allow for only 80% of core material as the most. You can adjust how much you allow of each of the different materials. And then our goal is, one of our next steps is going to be to run some SPH calculations to kind of calibrate what these parameters are, so that we can say, yes, this is a framework that works, and here's what we recommend using for different materials in order to have differentiated bodies. Like right now, we don't have layers beyond 2. It's like we ignore the crust. Nobody really cares about the crust anyways. So we ignore the crust, we just have the mantle and core, and then look at how much material from each of those things is spewed out in the collisions. So this is some of the results from the stellar evolution and tidal dissipation. Stanley Baronet was an undergraduate student when he did the development, and so Stanley and Noah were both undergraduate students when they did this development. And this is the paper that has that physics in it. So this just shows that you do get engulfment because of the interaction of the tides with different massed objects at different starting distances. The Yarkovsky effect. So this is Noah Farrick. He's my current graduate student. You'll recognize this is the same author list. It's just the first 2 have been switched. Noah led the effort on the adding the Yarkovsky effect. And so this is showing what is the evolution of the planet, or the orbital radius, depending upon what direction it's rotating, the obliquity, and the size of the object, the size of the asteroid. Because it's typically, this is something that affects asteroid-sized objects more than anything. And then this just shows what happens as the star evolves and what happens to the orbits of the planets. One thing I will point out is that we found there's some literature that exists that does the Yarkovsky effect that uses Mercury as the integrator, and there was a mistake there's a bug in the code. And so we talked to the author of that paper, and they're like, oh, yeah, that looks like a bug in the code. And so that bug has been removed in this rebound of the Yarkovsky. So anyways, the Yarkovsky effect is there. The next thing that we're working on, I just got a new graduate student who's going to be working on the Yorp effect. So Yarkovsky effect is for a spherically symmetric object, where the Yorp effect is for an asymmetric like something that has higher multipoles in its mass distribution. And what happens when you go from a spherically symmetric object to a non-spherically symmetric object is that now you have handles that you can exert a torque. So not only do you get the radiation pressure that changes the orbit, but you can change the spin of the object. And when you change the spin, it can change by a lot, to the point where you can fission. And part of the reason that I'm interested in this is that this is probably something that's going to be important when you pollute white dwarfs. When you pollute white dwarfs, you're getting material that's right next to the surface of the white dwarf star. If there's a tidal disruption, you're going to have objects of different shapes that come out, and then you're going to have, it's not that it's high intensity. Well, okay, so it's not that a white dwarf is very luminous. It's just that you're orbiting at like 5 Earth radii away from this object. And so the effect is that it's basically the same as a red giant with an asteroid in the asteroid belt, except that it's a white dwarf star and the material is right next to it. So it's roughly the same scale of an effect. And as a consequence, the Yorp effect, if you're going to get fission, then the rate that you produce the material that's going to fall onto the white dwarf surface is going to be different. And so that's part of the reason we're developing this, is to help model the late stages of the production of material that pollutes the surface of the white dwarf star, And we want to do that. We want to make those measurements because the white dwarf pollution is really the only way that we have to measure the bulk composition of the planets. And so I'm going to go out on a limb. It's the season to be provocative in the statements that we make. Since most of the atmospheres of planets are only, of rocky planets, is only a few percent of the stuff, then it should really only be a few percent interesting. And the bulk composition is where most of the material is. The last thing that we've been working on, and this is in collaboration with some geoscientists and cosmochemists who do modeling the materials that go into the formation of the different planets. So how do you, like, basically you start with some composition in the solar nebula, and then you change the pressure and temperature conditions over time, and different minerals are going to form at different rates and at different locations within the disk based upon the physiochemical conditions that exist in different spots. So there's this code that exists in the geoscience community called GRAINS. It's I think it's the most, I believe it is the most extensive chemical network, meaning that it has the largest number of input chemical elements, and it has the largest number of compounds that you can form from those chemical elements. Now, some of them aren't particularly important for the Earth, but they're tracers of other physics that are going on inside meteorite, like hafnium and stuff like that. Everything that's in red here, so rhenium, osmium, tungsten, everything that's in red is modeled in our code, in the GRAINS code. And then the dark ones are ones that have been measured in different bodies. So the reason that, one of the things that we wanted to do is, this is something that's basically, the way that it's been used by the cosmochemists is they just take a box and they have a composition and then they change the temperature in the box. And the composition stays the same, and they look at what forms and what are how much of one material do you get compared to something else? How much olivine do you get compared to Worcestershire-ite, or whatever the different minerals that are formed. But in a protoplanetary disk, the composition is going to be changing because stuff that's still in the gaseous form is going to advect with the gas, and that's going to change the composition radially within the disk. And so what we did in our group, and this was done by my postdoc at the time, Min Lee, is that we added a hydrodynamic simulation and then changed the composition as the gas moved around. So basically, we start with a disk with some, maybe there's a composition gradient or a chemical, so there's a chemical gradient, there's definitely a temperature gradient and a density gradient. And then some of the material will condense out and form dust that will decouple, so it forms basically planetesimals and decouples from the gas. But then you have some of that material that, while it's condensed, or like it's formed some minerals, it's still in the dust form or in a form that will advect with the hydrogen and helium. And so then the disk evolves, composition is now changed, you condense more material, you settle, like more material decouples, and so then you can look at what is the different composition of the planetesimals that you form as a function of radius and time. So this is the code that we've been working on. The original, so GRAINS, it's 33 input chemical elements and almost 800, like 750 different chemical compounds that are formed from those 33 initial elements. And this matters. There are a number of chemistry codes where they'll take like 16 input parameters, 16 input elements, and so there's a number of people in the Exoplanet community that are using those codes, but it turns out that there are some compounds that they're missing, and as a consequence, they misinterpret. You're missing a sink for oxygen or carbon or something like that in your chemical network because you're not getting the Fe2 manganese something or other element that actually absorbs some of the carbon out of the system, or some of the oxygen out of the system. So that's the code that we've developed. It is available. It's a little bit clunky to use right now because it was written in Fortran 50 BC, and we're working to kind of update it and make it a bit more presentable. We had to get a special compiler to get it to run. This is what happens when you develop code in the early 80s, and you keep adding to it without updating the software. So we're we're trying to figure out the best way to move forward on making this more user-friendly. But another thing that we're doing within this right now, so I just got another graduate student who's working on isotopic variations. So because isotope ratios, you have different isotopes of oxygen, that can be a really sensitive temperature measurement, is the ratios of oxygen 15 to oxygen 16 that you get. And that's how we do it with the ice cores in Antarctica, is, you know, what's the ratio of carbon 13 to 14 in the CO2, and then that gives you or not 13 to 14, but oxygen 15 to 16 in the water, and that tells you much more detailed about what the actual temperature is when the ice was frozen. So we're doing the same, that kind of same thing in order to explain what is the composition of the different meteorite families that you have in the solar system. So here's some results from that. So this, for example, over here shows over time. So this is time goes from the thin to the thick lines for silicon and for calcium as a function. So you look at silicon to calcium as a function of time, and then this is the surface density of condensed silicon or condensed calcium. And you can see that you start in a given region, and then you have this front as that material condenses and the disk evolves, where the solid material forms from. And then right now we're comparing it to some subset of the chondrite families. We're expanding our analysis to other asteroid family or other meteorite families. So a few things that we've learned from this is, one, that we're not able to reproduce the solar system composition if we just assume constant viscosity disk. The disk doesn't get hot enough to reproduce the meteorite compositions that we see. So there has to be something else going on. So our initial disk that we used was something that was done by, I think, Phil Casson, I think is what it is. He's a scientist at NASA Ames. He did some stuff in the 90s, and he was able to reproduce the chondrite composition. But if we added a more sophisticated disk, where it's, instead of just an analytic model, it's a model that has a viscosity and the temperature fluctuates or varies based upon how the gas interacts with itself, then we're not able to get a disk that's hot enough to produce the chondrites. So we had to go even more sophisticated than that. And we did an outbursting model. So there are a number of stars as they go through their adolescence, they have big outbursts, and like the FU Orionis outburst. And so what will happen is you build up, get a bunch of material, it's coming in, there's friction within the disk, it gets hot enough to ionize the gas, and then once the gas gets ionized, then it all of a sudden couples to the magnetic field, and you get a big burst of accretion onto the star, and then the star's luminosity goes way up, and then that increases the temperature everywhere. It depletes the inner disk, and so now you don't have as much friction, and so the disk cools down again until you can build up more material, comes in, and then you get the friction, heats it back up again, it reionizes, and then you get several episodes of high accretion, which corresponds to several episodes of stellar outbursts, which corresponds to several episodes of really high temperatures that then drop back down. And so we had a disk where we're modeling these. So here's the temperature spikes. You get these different temperature things. They last for about 100 years or so. And what happens is that you can get, at different distances, you can get really high temperatures to where you would re-vaporize all of the grains of minerals that you form. And our goal, so we're still trying to ramp back up. The person who was working on this moved on, and so now we have to find something else. But the goal with this is to try to figure out a number of things. One is this sufficient to reproduce what we see in the solar system, and then how does it map to other planetary systems? Because, for example, if you look at the snow line, so here's the snow line. Let's just look at this side where the spikes are a little bit more separated. So here's the snow line. That's where water ice will evaporate. And you can see that you get several episodes where the snow line goes out beyond 10 AU, and it comes back in, and then it goes back out beyond 10 AU, and then back in and back out. And so if you're forming planets out of condensed light molecular fluids, you'll have episodes where the planet can accrete material, and then it's all gaseous again, and then it recondenses, and then you can get more. So that's going to affect like giant planet formation. And more interesting, especially for us, because we're looking mostly at rocky planets, is that you can get the rock line to fluctuate around 1 AU. So you can go between where rocky material will condense and form planetesimals, and then where they evaporate again, and where they recondense and re-evaporate. Part of the reason why this is important is because we still don't really know the origins of calcium aluminum inclusions. So CAIs in the meteorites they're older than the meteorites. So the oldest condensed material we have in the solar system are these CAIs, and they show they're weird shapes. So instead of forming like little grains that are like little spheres, they're strange shapes, which means that they've had a troubled history of maybe some kind of, like, they've been melted and then refrozen, then remelted and refrozen, or something's going on around them where they get bumped into and that changes their shape. So there's some stuff about the past of these CAIs. We don't know really where they formed. We don't know what their history is like. All that we know is that they're older than everything else. They're older than and it's like hundreds of millions of years older than the chondrites. So not hundreds of millions. They're hundreds of thousands of years older than the chondrites. So this might be a way of producing them. The other issue is that we find them in meteorites that exist outside the orbit of, like, out by Mars, and yet the prevailing model for how they're formed is that they form right next to the stellar surface. And so dynamically transporting stuff from the stellar surface out to be on the orbit of Mars is not really that trivial. And with this model, if it works, then we're actually forming it as an AU. And an AU is it's a lot easier to move something from 1 AU to 2 AU than it is to move it from 0.1 AU to 2 AU. So anyways, this is something that we're pursuing in our group, is looking at how these stellar outbursts might affect formation of what materials goes into the planetesimals, and also some of the details of the composition of those planetesimals. A few last things that my group has done using these tools is, for example, looking at TRAPPIST-1, formation of TRAPPIST-1, because everybody and their dog is looking at it, so we might as well join the party. So this was using pebble accretion to form the TRAPPIST-1 system, but also using our collision and fragmentation code that broke things apart and then reassembled them as time went on, and we were able to kind of reproduce a number of systems that looked like the TRAPPIST ones. So the TRAPPIST planets are the orange ones, and then the systems that we produced are the blue ones. Another thing that we're looking at in our group is modeling. This is also looking at TRAPPIST. It's one of the prevailing assumptions that goes into a lot of exoplanet science is that the planets are going to be tidally locked. The issue is that that's just not true, especially in a system like TRAPPIST, where you have a lot of strong dynamical interactions between the planets. So the orbital periods are fluctuating on relatively short timescales, and so the planet can't re-lock. Like, the rotation of the planet, the rate of change of the rotation of the planet from tides is much slower than the rate of change of the orbital period from the resonances. So the orbital periods are changing faster than the planets can respond through tides. And as a consequence, you're going to get periods of prograde rotation or retrograde rotation, depending upon how the orbital period is changing relative to the planet. You get some situations where it will librate, but it won't librate for very long, and then they'll start to go into a rotation phase. And so these planets are all habitable, or like so many of them are habitable in quotation marks. And so now you're talking about, okay, you've got liquid water on the surface, or some of it's liquid and some of it's frozen, but now you're changing whether you have one side of the planet always staring at the star, or if it's rotating slowly, or if it's the opposite side. And so we're looking at what is the histogram of how long it spends in each type of state, whether it's librating or whether it's rotating prograde or retrograde relative to its orbit. And then, so this paper by Cody Shakespeare was looking at how does the climate change by changing the insolation and the reflectivity off of the different surfaces. So, and then the last thing, this one is coming out. They were a little distracted by a different project that came up, but this is coming out fairly soon, which is looking at basically taking Magrathea and analyzing the TRAPPIST system using our Magrathea code. So that's basically what I have for you. So I guess the moral of the story is we have several tools that we've developed for rebound for n-body integrations that includes stellar parameters, like changing stellar parameters or changing planet parameters. You can imagine changing the albedo, for example, of the planets they orbit. We have things that do the fragmentation after collisions. We have tools to track the composition of those fragments. So as you have these bodies that are interacting with each other, their composition is going to change. And we have the Yarkovsky effect, and we're adding the Yorp effect to rebound. We have Magrathea, which is a planet interior modeling code that's designed to be really easy to use. One undergraduate day was, my original claim was that it was going to be one undergraduate afternoon, but after some testing, we found that it's actually more of an undergraduate day to get it up and running. And then we're also preparing this chemistry, like the disk chemistry code, to be released to the. Thank you for your time. I appreciate it. I'm happy to answer any questions that people have.
All right, yeah, so awesome talk, Jason. So we definitely have time for some questions. So if folks online want to raise their hand, or you can also post questions in chat. Elisa, I think I see you have your hand up.
Hi, Jason. Awesome talk.
Hi.
Really cool stuff that you're adding to Rebound. Have you thought about, or can you model like the pre-main sequence stage of M dwarfs and with the stellar evolution part, and sort of model like the evolution of like the habitable zone for some of these low mass planets?
So if you have, so that capability is kind of independent of what we did with Rebound. So if you have a model for here's the evolution of the formation of a M dwarf or something like that, we can add it in. So it's an arbitrary parameter. So you can have the star mass grow. One challenge would be you'd have to incorporate probably gas drag into the system, but that is also something that exists in Rebound. And so if that was something you wanted to look at, what would be really interesting is to do that with also, like modeling where's the habitable zone, and also how much are you baking the water out of the system as you form the. So all those capabilities, I think, should be in there. If you have a model of the formation of the star, putting it into Rebound will be a matter of providing a table of whatever parameters you care about, and including whatever effects those are going to cause. Like if it's going to cause a gas drag, for example, then you would incorporate the gas drag module that already.
Okay, that's always been something. It sounds like an interesting problem, and it sounds like there's a lot of the tools folded in are what you've been adding. So that's great.
Yeah, so I think if you have the model for what happens with the star, then you can do it with the code that we developed.
Cool, thank you.
Great. Ed, does anyone else have questions also in the room?
In terms of your disk condensation code, obviously there's a huge amount of work being done in hydro simulations of different types of disks, different temperature gradients, different viscosity variations based on evolution of disks. Are you hoping to be able to integrate your condensation code with more complex disk evolutions of different stellar types or masses, or so forth?
Yeah, so one of the main collaborators with us on developing that code is Xiaowan Zhu, and he works on Athena++. He's one of the main developers for Athena++. So right now, the disk models that we have been looking at are all cylindrically symmetric, but it does include things like dead zones and like where things are ionized and stuff like that. At least Okay, so the disk that we're using most often now is a fairly straightforward analytic disk because it does pretty well already. But the goal is to be able to use more sophisticated results, including some of these effects. Like one of the things that we didn't incorporate in our first outbursting disk model is a self-consistent opacity, where you ionize something and now the opacity goes way up, and so we have a kind of a recipe that does that. It's a recipe that we can blame someone else for developing it because it was done back when we didn't have the tools really to do it self-consistently. And so we are working in that direction. It's a matter of having the right warm body working on the problem. In terms of doing like a 3D calculation, that we could do it, but that's a lot of extra computation, because the most expensive part is actually the chemistry. Like the disk evolution is 1,000 time steps or something like that. It's fairly simple. Chemistry is what takes the most time, and so doing all these boxes in 3 dimensions is probably not worth it right now. But we are looking at improving our one-dimensional disk model to incorporate some of these.
So I had a question back at the beginning when you were talking about the ice transitions.
Mm-hmm.
You mentioned Ganymede, but I was curious, have you looked to see if this new phase of ice that you're finding is applicable to the theorized high pressure ice layer at the base of the ocean on Ganymede?
So this is usually higher pressure than what Ganymede itself would produce, because Ganymede, you're looking at something that's like 1% the mass of the Earth.
Yeah.
And so you don't really get up to the, let's see, I have let me phase diagram. So, this one. So you're looking at, if you go another factor of 10 down, then you're still looking at like I6 as the prevailing layer. So this it's not really an effect that would happen on the moons in the solar system because the pressures aren't high.
Fair enough.
But it is important, because right after we did this was when that paper came out that said it looks like there's kind of 2 types of like water-rich and water-poor planets in the small planets.
Yeah.
And so it would certainly affect the water-rich component of that study. The figure on the right is a slice of the mass-radius relationship that just shows that we can incorporate our systematic uncertainty calculation. So this is like 1,000 realizations of this. It's a zoom in of a figure that maybe it's not in here. It's a portion of the figure where this diagram came from.
Well, while we're on this, I was curious if you all have the capability of doing, so this is the diamond anvil. This is great that you're working on these phase changes, but is there any capability right now or any plans for the future of doing torsion experiments on ices to measure things like shear modulus and shear dissipation in ices?
So I don't know how that's done, because the diamond anvil cell is really static.
Yeah.
So I'm not sure how that would be done. I guess I could take it back to see.
Yeah, there's like these like torsion machines that they use but in my experience, everyone's doing it on silicates, and there's very little research done on ices. So there's a lot of uncertainties in some of these factors, like shear dissipation in ices, especially at high pressures.
So if I were to, I'll have to think about this. Let me come back to that question real quick.
Sure.
So one of the reasons, I'm going to go back to what you said. One of the reasons we showed this, or that we showed this figure when we did it, is because with the systematic uncertainty, that changes what claims you can make about the composition of the planets that you're modeling. I think a little too frequently in exoplanet science, we make assumptions about like what the composition of we don't make definitive statements such as this planet cannot have more than this much water in it. Instead, we kind of try to go for the jugular unjustifiably by saying, well, if we assume all these other things, then this is what the composition is, as opposed to this is the the weakest claim that we can make is that this planet can have no more than this percentage of water in the composition. That's the direction that I think we should be making our statements, because they're more realistic. Or I guess they're more honest in terms of what we actually know and what we don't know. Going back to what you're saying. So I don't know how, like I know, if I pulled out some memories from 23 years ago, I used to work in a torsion pendulum experiment. And it turns out you can make much better measurements of the torsional properties of the solids if you can get a really thin fiber, and then you put a torsion pendulum on it, and then you measure the harmonics of the twisting, like the noise and the twisting modes of the fiber. And so I'm thinking, like, ice is, so you can't really, I guess, try to make, I don't know how I would do that. It was the difference between having a thin fiber with a really sensitive setup like that is that you can make like thousands of times more precise measurements of the torsional properties of the solid than you can make with kind of a bulk object that you're twisting.
Right.
So that's all that I've ever done in that area.
Yeah.
In terms of like what's the material science of these things. I don't know. I could imagine producing something kind of like that with ice, but ice is really brittle too. So
That's probably why there's not been a lot of work done on it.
Yeah.
But I'm not an experimentalist, so I just am handing the question off to you. And
like with silica, I mean,
it
they'll have like sapphire fibers and
Yeah.
they'll have fused silica fibers and things like that. Those ones are a little bit more resilient when it comes to twisting modes. I'll have to, I can't say. In terms of doing it at these pressures, because this is at like 100 GPa, which is, in order to get 100 GPa, you have to have small volumes because the energy density is really high. So we have a big press at UNLV, like a large volume press, but a large volume press is like 6 millimeter. So I don't know what, and that can't go to, okay.
Yeah, I think even at the not as high pressures would be helpful. There's really not.
Yeah, because if you're looking at surface ice and how the surface ice affects the Q of the system.
Yeah, I mean, surface are just, at just not as extreme pressures. It'll be helpful.
Okay.
Yeah, something to think about.
I'll take it back to the powers
yeah,
that be.
sounds good. We can talk about it more. Well, we're just about at the time, so I'll just give one last chance. Anyone online or anyone in the room have a final question for Jason? I'm not seeing any, so I think we will call it there. So Jason, thanks again for the great talk.
Thank you.
And thanks everyone for coming out. I'm gonna end the call here.